So my name is Nur Jaslini binti Muhammad Shukri. My metric number is 083208. So today I will briefly explain of our smart building management system. This system was developed and simulated as a distributed system to monitor building condition in real time, including temperature, lighting, and HVAC. We use Java meter reading so that each sensor can run independently and simultaneously. This allows concurrent data collection from different rooms, such as a room A and room B, without delay or interface. In addition, we implemented a distribute hash table or DHT to manage and store the data across multiple distribute nodes efficiently. We also apply simple naming strategy to identify and organize sensor reading clearly within the system. All sensor activity are displayed through real-time console output, showing live update of the system. Overall, this project demonstrates key concepts of distributed system, including concurrent processing, data storage, and system architecture in a smart building.
Basics process handling. This slide explains the basic process handling in our smart building management system. Our system uses Java multi-threading, which allows multiple sensors run simultaneously. This supports real-time monitoring because each sensor can collect and process data independently without waiting for other sensors. Sensor simulation. We simulate 3 different sensors in the system. First, temperature sensor. Detect temperature between 60 Celsius and 30 Celsius. Update data every 2 seconds. 2. Light sensor. Detect whether the light is on or off. Update every 3 seconds. System architecture. This slide shows architecture of our smart building management system. First, there are 2 rooms equipped with sensor. Room A contains a temperature sensor with a range of 60 Celsius to 28 Celsius and a light sensor. Room B contains a temperature sensor with a range 23 Celsius to 28 Celsius and a light sensor. Next, the data flow process. The system uses multi-threading, which allows all sensors to send data simultaneously. This means the system can process multiple sensor reading at the same time without waiting for one sensor to finish before handling another. After that, the sensor data is passed to a hash function. The hash function converts the incoming data into a unique key. This key determines which node in the distributed hash table which store the data. The system has 3 DHT nodes, node 0, node 1, and node 2. Each node stores part of the sensor data based on the generated hash key. This helps distribute the storage workload evenly across the system. Finally, the stored sensor reading the displayed in the console output, allowing users to monitor the sensor data in real time. System architecture. This slide shows architecture of our smart building management system. First, there are 2 rooms equipped with sensor. Room A contains a temperature sensor with a range of 60 Celsius to 28 Celsius and a light sensor. Room B contains a temperature sensor with a range 23 Celsius to 28 Celsius and a light sensor. Next, the data flow process. The system uses multi-threading, which allow all sensors to send data simultaneously. This means the system can process multiple sensor reading at the same time without waiting for one sensor to finish before handling another. After that, the sensor data is passed to a hash function. The hash function converts the incoming data into a unique key. This key determines which node in the distributed hash table which store the data. The system has three DHT nodes, node 0, node 1, and node 2. Each node stores part of the sensor data based on the generated hash key. This helps distribute the storage workload evenly across the system. Finally, the stored sensor reading the display in the console output, allowing users to monitoring the sensor data in real time. Implementation and code. Code class temperature sensor eccentric, class light sensor eccentric, class HVAC sensor eccentric. This class represent different sensors in the smart building system. Each class eccentrics allowing system to run independently. Temperature, light, and HVAC monitoring can operate simultaneously. Start treats code T1.start, L1.start, H1.start. This command start all sensor treats. Each sensor begins collecting and processing data at the same time. The system does not need to wait for one sensor to finish before another starts. Real-time monitoring. Code 3.sleep. The system pauses for 2 seconds before reading the next sensor value. They simulate real-time monitoring in a smart building. DHT storage, node 0.store key value. Sensor data is stored in a distributed hash table. A key determines which node store the data. Console output. Code system.out.println. Time room A. Display sensor reading on the console. Allow user to monitor system activity in real time. Show temperature, light status, and HVAC action. For output, room A temperature change from 28 Celsius to 60 Celsius. When temperature is high, HVAC change to cooling. When temperature is low, HVAC change to heating. Light sensor detect on-off condition in both rooms. The message will successful indicator the simulation is executed successfully.
Assalamualaikum. My name is Nur Adila Sofia Petrosmadi and my metric number is 079315. Section explain how naming and lookup resolution are simulated in the smart building management system. The system applies a structure naming strategy together with a simplified DHT approach. Each sensor reading is assigned a structure name that contains the sensor type, room identifier, and measurement or status value. This helps organize and identify sensor data more clearly within the distributed system. After sensor data is generated, the Java hashcode method is used to convert the combined room identifier and sensor value or status into a numeric key. This key determines which nodes in the system will store the data. The modulo-based hash condition is then used to identify the responsible nodes. This process helps distribute sensor data across multiple nodes instead of storing everything in one location. The system contains 3 nodes, which are node 0, node 1, and node 2. When a sensor generates data, a hash key is created and the node checks whether it is responsible for storing the key. If the node is responsible, the data is stored locally. Otherwise, the requests are forwarded to other peer nodes. Although a dedicated lookup method is not implemented, this simulation still demonstrates the basic concept of distributed data retrieved through peer node checking. The naming and lookup mechanized is implemented using several Java methods. The hashcode method generates unique key. The store method store or forward data, and the responsible method determines which node should be managed the key using modulo-based hashing. Overall, this simulation demonstrates the basic principle of distributed system, including decentralized data storage, scalable nodes management, hash-based distributions, and peer communication between nodes. That's all from me. Thank you.
Good day, Doctor. For this slide, I'm going to explain the core differences and architectural traits of between our two consistency models: sequential consistency and eventual consistency. First, sequential consistency is rely on synchronous replication. This means whenever a sensor writes data, the system waits for all nodes to copy the updates before finishing the task. Because of this blocking behavior, it is slower but highly accurate, ensuring there's zero stale reads across our network. On the other hand, eventual consistency uses asynchronous replication. The primary node saves data instantly, and the updates happen later on the backup nodes using background threads. This model makes the system much faster and responsive. I will explain our replication process workflow. First, a sensor thread generates data and sends it to node 0. The system automatically hashes the data key using the hashcode method to create a structure number. Next, we select the responsible node using our formula, which is key mode 3 equals to ID mode 3. This saves and distributed data records evenly across the cluster. As seen in ePass, which is my teammate's console image, node 0 logs temperature for room B, while node 1 and node 2 at the same time handle light updates from room A. Since environmental change happens slowly, a minor delay in updating backups nodes has very little impact on operations. This keeps our pipeline highly fast and responsive. Thank you.
Hi everyone, now I'll be explaining on what's happening during the simulation. For this part, I'll be breaking into 3 different parts, and the first part is simulation initialization and data collection. At beginning of simulation, the system creates a distributed cluster consisting of 3 storage nodes, which is node 0, node 1 and node 2. After the nodes are initialized, 6 sensor threads are started concurrently using Java's start method. These sensors represent temperature, light, and HAVC monitoring for both room A and room B. Each sensor runs independently and collects environmental data at different polling intervals. For example, temperature sensors collect data every 2000 milliseconds, HVAC sensors collect 2500 milliseconds, and light sensors collect data every 3000 milliseconds. Whenever a sensor collects a reading, it creates a data record and generates a unique key using Java's hashcode method. This key is later used to determine whether the data should be stored within the distributed cluster. Next, we will look into data routing and distributed storage. Once a sensor generates a data record, the information is sent to node 0 through the store method. Node 0 acts as an entry point for all incoming data and determines which node is responsible for storing the record. This is done using a modular-based partitioning formula which compares the generated key against node ID. If node 0 is correct destination, the data is stored locally. Otherwise, the node 0 forward the data to appropriate peer node, which is either node 1 or node 2. This process ensures the data is distributed evenly across the cluster instead of being concentrated on a single node. Throughout the simulation, the terminal displays live telemetry logs showing sensor readings, routing, decision, and node responsible for storing each data record. The third part is replication and simulation completion. So after the data has been stored, the system performs replication to improve reliability and fault tolerance. In eventual consistency mode, the responsible node stores the data immediately and allows sensor thread to continue without waiting. Replication is then handled asynchronously by background threads. These background threads introduce random delays to simulate real-world network latency before copying the data to other nodes in the cluster. So each sensor thread completes a total of 5 monitoring cycles. Once all cycles are finished, the main application uses the join method to wait for every thread to complete the execution. Finally, the system displays a simulation complete message and shut down cleanly, ensuring that no background processes or memory leaks remain. Next, we will look into 4.4, which is example output. This screenshot shows the live console output generated during the simulation. So, as the sensor threads run concurrently, the environmental data from different rooms is continuously collected and processed. So the output displays how incoming data is routed and stored across the distributed cluster. For example, node 0 stores climate-related information from room B, while node 1 and node 2 simultaneously handle lightning updates from different rooms. So the real-time console message confirms that multiple threads are operating at the same time and that data is being distributed correctly among the storage nodes. Overall, this output demonstrates that the smart building management system successfully implements multi-threading, distributed storage, and efficient load balancing without causing performance bottleneck.
Finally, let's look at our simulations output. Our console log shows different sensors like temperature, light, and HVAC sending data at the same time. For example, node 0 saves data for room B, while node 1 and node 2 handle light setting for room A. Based on this, we recommend eventual consistency for smart building system. Since room temperature or light levels change slowly and very slowly, a minor delay in updating backup nodes has very little impact on the system. Saving data immediately keeps the system fast and prevents busy sensors from dropping important logs. That's all for my part. I will pass it to my teammates.
So, as the conclusion of our Smart Building Management System project, the system demonstrates distributed system concept using Java multi-reading to enable simultaneous monitoring of temperature, lighting, and HVAC in a room A and a room B. Sensor run concurrently without interruptions, allowing real-time data collections. We implemented a distribute hash table to store and manage data across multiple nodes using hash and peer communication. The system also applies event-driven consistency to improve scalability and responsiveness. Overall, for this project, show how distributed system can support efficient, real-time smart building monitoring.